Good day, calculus students, and welcome to this Going Deeper video on the basic area between curves formula. Now, we'll have this formula in class, and you might say, that's all I care about. Just give me the formula, and I'll use it to compute areas between curves. And that's fine. But for those who want to know more of what's behind this formula and why it always works in the basic situation that we'll talk about, that's what this video is for. And of course, understanding why things work can often give you that extra edge in situations that may be a little more unfamiliar or unexpected, to be able to adapt how things should work in situations like that. It works a lot better if you know what's going on behind the scenes. So let's take a look. First of all, this basic area between curves problem is a situation that you see described with the setup here, where the graph of one curve is always going to be above or at the graph of the other curve. We can see that because f of x is greater than or equal to g of x for all x in the interval that we're considering. That means that the graph of f will be the top graph, and the graph of g will be the bottom graph, and there's no switching here. So that's our basic area between curves problem. Okay, well then we have the formula for computing that area. It's just going to be the integral from a to b of f of x minus g of x times dx. Now, in class, we will have a diagram that will provide some intuition for why this should be true. It would probably be believable, but of course it is a special case. It's only describing one situation, and you sort of have to wonder, what about other situations? How do we know this is always going to work? And that's exactly what we're going to address on the next slide here. So how do we know that this formula works in all situations? Now, I'm going to try to use one diagram that covers all possible situations. It's kind of ambitious, but it's a good challenge for me. Now, I did pre-draw this diagram in here to take a little bit of the challenge out of it, because of course this is going to be a little complicated to cover all three cases. So again, the diagram in class will just cover one case, the simplest cases. And that has to do with the rectangles that we are using here to approximate the area between the two curves. Okay, we can approximate that with rectangles. I'm assuming that's a relatively familiar strategy from Calculus 1, that you approximate each little strip of a region with a rectangle, and then you add up the areas of the rectangles. That gives you an approximation for the overall area, and then of course we could take a limit, but let's deal with the rectangles first. So our first scenario will be when we're over here on an interval like this, where the graphs of both f and g are above the x-axis. You can see the graph of f in purple, the graph of g in green, and the region, hopefully, I'm not going to try to shade it in because that would make this even messier than it's going to be already, but the region here is bounded on the left and right by the yellow, and on top by the purple, and on the bottom by the green. Okay, so on this interval that we're looking at here, which, by the way, we will say that our interval has width delta x, so that'll be the base for our rectangle, and that will be consistent across all three cases. Delta x, we're always taking as a change in x as the base for our small rectangle. Now, it's the heights where things get interesting here. So if we look at our approximating rectangle here, okay, there it is. Okay, our approximating rectangle is going to look like that. And by the way, we'll use right-hand endpoints here for obtaining the heights of our rectangle. So you can see that the height of the rectangle goes between the graph of g and the graph of f on the right-hand edge of the rectangle. And let me put the other rectangles in here right away as well. Okay, so I did not place my region R very conveniently here. I'm actually going to erase. Let's see, I don't know if I can erase that anymore. Nope, I can't. Just got to live with it. Okay, so let's put our rectangle, right about here. Okay, so on this interval, our rectangle that is going to approximate the area of that strip of the region will look like so. Again, with delta x and the height going from blue to purple. And then we have the third situation over here where both graphs are below the x-axis. Here our rectangle is also going to be entirely below the x-axis, and it will look about like so. I should have mentioned in the second case we have one curve above and one curve below the x-axis, so there our rectangle straddles or crosses the x-axis. So these are our three scenarios, and what I aim to show you is that in fact the height of the rectangle can always be represented by the exact same expression no matter how that rectangle is situated. Okay, so to represent this, it's really going to be good to get another color involved here. So let me see if I can switch colors for my pen here, and let's switch to blue. Okay, so what we see, if we want to describe the area of, or the height of our first rectangle, we have, yes, we have our height going between the green and the purple. Now the height up to where our rectangle begins, that is going to be the y coordinate on the graph of g. And as you know, the y coordinate on the graph of a function, where the independent variable is x, that is just the value of the function there. Okay, so we have g of xi up to get up to where our rectangle starts. And then, let me put over here to get to the top of our rectangle. Well, the top of our rectangle is all the way at, is where it hits the purple curve on the right edge there. And we know that that is going to be f of xi, the value of function f at xi. That gives us the y coordinate for this particular point on the graph of f. So to get the height of our rectangle here, the height of the red portion, well, we could start with f of xi going all the way up to that purple curve, but we have some extra here that we don't want, right? We don't want this portion, so we subtract that off, and we find that the height of our rectangle then, that red portion, is f of xi minus g of xi. Okay, that's what happens when both functions are non-negative, when everything is above the x-axis, and that's probably the easiest situation to see what is going to happen. Well, let's switch to our second scenario here with that middle red rectangle. And here we have a situation where one curve is above the x-axis, the other curve is below. And what we would like to do is get the height of our rectangle here. Okay, and in this case, we'll do it in two portions. So we have our height from the x-axis up to the purple curve here, and like we discussed before, that is going to be f of xi. Okay, now we also need to include in here the height of the portion of the rectangle that is below the x-axis. Okay, and that is going from the x-axis down to the graph of g. But this height is not going to be g of xi, because you see g of xi here would be negative. And can the height of a rectangle be negative? No, of course not. Okay, so what we have to do is adjust the sign there here, and we see that to make sure that height is positive, we have to stick a negative sign in front of g of xi, and when we take the negative of a negative, we get the positive. Okay, so that's what a coordinate of a point means when that point is below the x-axis, right? The coordinate is not the distance, it's the directed distance, and you have a minus sign in there saying, yeah, we went down instead of up. So we just negate that again to make it positive, and negative g of xi is the height of that portion. So now we want to add those two portions of the height together to get the total height, and so that would be f of xi plus negative g of xi Okay, and of course, as we know, that I is supposed to be a subscript, by the way. As you know, adding a negative is the same as subtracting, so we could say this equals f of xi minus g of xi. Okay, and so there is the height of our rectangle in this situation. As you notice, we expressed it exactly the same as we did the height of the first rectangle. Okay, well, I wonder what is going to happen in the third scenario when both curves are below the x-axis, so the values of both functions are negative. Let's take a look. Okay, so here we again would like to get the height of our rectangle, which is going to be that length right there. And let's see, I probably should put that on the other side because, of course, we have to get that. We have to go all the way down to the graph of g of x, our bottom graph. And this is still below the x-axis. So just like we saw before, one of these times I'm going to hit it. There it is. Just like we saw before, that's not g of xi. It's going to be negative g of xi to get all the way down to the green graph from the x-axis. But then we have a portion here that we don't want, which is the portion that it took to get us to get down to the purple graph, the graph of f. So that is going to be negative f of xi here, because now that f is also below the x-axis, the height, the distance to get from the x-axis down to the purple graph, the graph of f, that also has to be negated because f of xi is going to be negative, indicating the downward direction there. Okay, so now, what is the height of our rectangle in this situation? Well, we want to go all the way down to the green graph. That's negative g of xi. Okay, but then we want to subtract off the part that we don't need, which is the part that we have to go down to get to the graph of f just to get started. So we want to subtract off that distance, which is negative f of xi. Okay, better put some more parentheses there. And now, as you know, subtracting a negative, that is the same as having a positive. So we can rewrite this as just, okay, the minuses will cancel, and we'll have f of xi, and then still negative or minus g of xi. And so just like in the other two cases, we see that the height of that rectangle, sure enough, can be represented by f of xi minus g of xi. Okay, so the height of the rectangle in all cases is f of xi minus g of xi. Value of the top curve function minus the value of the bottom curve function. Okay, well, once we've got that nailed down, it's pretty quick to go from there to the formula. And so let's do that. Okay, so the area of each approximating rectangle, remember that they all had base delta x. So since they all had height that could be described by f of xi minus g of xi, even though it looked different in different scenarios, we can always represent it that way. We just have to take that base, or that height, times our base, which is always delta x, and that gives us the area of the approximating rectangles. Okay, so what if we want to get an approximation for the area of that entire region R between those two curves? Well, to get that, we add up the areas of our approximating rectangles. And as you know, we can do that, get a Riemann sum in here. So let's do that. This will be the sum as I goes from 1 to n, assuming that, as typical, we're using n subintervals and hence n approximating rectangles. We add the areas of those approximating rectangles together. And there they are, as the area of each one, and just add them all up. And this gives us an approximation for our overall area. Now, as you know, if we were to use more subintervals and then more rectangles, they would all be narrower, delta x would be smaller, and our approximation would get better, because as we saw from the these heights here were certainly not entirely representative of the strips of the region. We're missing some area. Here we have some area that is sticking out from our region. And the reason that that is so prominent is because of the width of our intervals. If we had narrower intervals, there would be less stuff missing, less stuff sticking out. Our approximation would get better. And so if we want to take that to the ultimate extreme, we can let the number of subintervals approach infinity so that the width of the rectangles shrinks towards 0. You might say becomes eventually infinitely short. Okay, so that then is the exact area is just going to be the limit as n approaches infinity of these approximations of the areas given to us by these Riemann sums. So it looks like that. And what is that? Well, hopefully you recognize it from Calc 1. That, by definition, is an integral. So we could also choose to rewrite this as the integral from a to b, the interval that we were doing our approximations over, of f of x minus g of x dx becomes a differential. Okay, and there you have it. The area between curves in the basic case, this always works, wherever those curves may be situated relative to the x-axis. I will say one more thing here. In our scenario, we did use approximations. So I was using intervals of width delta x, a regular finite width. Another way to do this would be to use infinitely small widths for our rectangles. Then we would do dx, but I decided to go with the approximating approach for this particular video. Okay, there you have it. Hope you enjoyed going deeper on the area between curves formula, and hope that that will serve you well and help you understand better what's going on behind the scenes. See you soon.